In this video, I will work out some examples of how to use L'Hopital's rule to compute limits. In the previous video, I already explained the statement of the theorem carefully, and I will link it in the description. Now it is time to do some actual computations. These are the three limits I will compute. I invite you to pause the video and give them a go. Then continue watching. First, I want to compute the limit as x approaches infinity of x over ln x. This is a quotient. I'll look at the top and the bottom separately. The limit of the numerator is infinity, and the limit of the denominator is also infinity. As x approaches infinity, ln x approaches infinity. So I have an indeterminate form of type infinity over infinity. This is precisely the kind of situation where L'Hopital may be handy. So I'm going to use L'Hopital, and I'm going to put here an asterisk to remind myself that I am using L'Hopital. And let's see what happens. If I use L'Hopital's rule, I need to compute the limit of, in the numerator, I'm going to take the derivative of x, which is 1. In the denominator, I'm going to take the derivative of ln x, which is 1 over x. Now, strictly speaking, I cannot yet say that these two things are equal. Every time I use L'Hopital, what I'm doing is saying, I'll finish the calculation, and if this comes out to be a number, or infinity or minus infinity, then the original limit is equal. That's why it's good to remind myself that I'm doing this. But in this case, it's short. After I do this, I can rearrange this nested function as x, and as x approaches infinity, this limit is simply infinity. So yep, I got infinity, therefore the original limit is equal to infinity as well, and I'm done. For my second example, I want to compute this limit as x approaches 0. It is a nice quotient. I'll look at the top and the bottom first. In the numerator, as x approaches 0, I have 1 minus 1, that is 0. And in the denominator, I have 0 minus 0, that's also 0. So I have an indeterminate form of type 0 over 0. Perfect, that's the one I can use L'Hopital's on, or at least I can try. And I am reminding myself I am using L'Hopital. So I get the limit as x approaches 0 of. In the numerator, I take the derivative of the numerator. The derivative of cosine is minus sine, and the derivative of minus cos 2x is plus sine 2x times 2. In the denominator, I take the derivative of the denominator. I have to use the product rule on x e to the x. Its derivative is 1 times e to the x plus x e to the x, and the derivative of minus x is minus 1. Let's see what we got now. I have a quotient again. The limit of the numerator is minus 0 plus 0, so it's still 0. And the limit of the denominator is 1 plus 0 minus 1, that's still 0. So I still have 0 divided by 0, an indeterminate form. I don't know if this is helping, but why not try to use L'Hopital's rule once more? And now I have the limit as x approaches 0 of. In the top, the derivative of the top. The derivative of minus sine of x is minus cos x. And the derivative of 2 sine 2x is plus 4 cos 2x. At the bottom, the derivative of e to the x is 1. And the derivative of x e to the x, I use the product rule again. So 1 times e to the x plus x e to the x. And the derivative of minus 1 is 0. What do we got now? In the numerator, the limit is minus 1 plus 4. That's 3. In the denominator, the limit is 1 plus 0. That's 2. Great, we got it. So the final limit is 3/2, which is a number. Therefore, this use of L'Hopital was legal. And the second limit is also 3/2, which is a number. Therefore, this use of L'Hopital was legal, and the original limit was also 3/2. We are done. This is my third example. The limit as x approaches 1 of x cubed minus 2x plus 1 over x squared plus 3x plus 2. Well, let's check first if I have an indeterminate form. As x approaches 1, the numerator is continuous and has limit 1 minus 2 plus 1, which is 0. And the denominator is also continuous and has limit 1 plus 3 plus 2, which is 6. I don't have an indeterminate form. I can simply plug it in. This is a nice continuous function. I'm not dividing by 0. So the answer is 0, and I am done. There was nothing else to do. This is an example in which I don't need L'Hopital's rule. And more importantly, I am not allowed to use L'Hopital's rule because I don't have an indeterminate form. If you try to use L'Hopital's rule in this case, you will get a wrong answer.